We will discuss now the next part, which is the capacitance for the MOS transistor. And if we look at the MOS transistor, it has two capacitances, gate capacitance and diffusion capacitance, and we will discuss every one of them separately. Now, capacitance are important for two reasons. Number one, delay, they impact the delay of the device. We will see this in next chapters, and they impact as well power and energy. Okay, so these are two important factors where capacitance comes in place. So the CMOS device, the gate has a capacitance, and the gate capacitance can be either channel capacitance or an overlap capacitance. The channel capacitance is the dominant one, about 90% of the gate capacitance, and the overlap is about 10% at best. In fact, a lot of people, they kind of ignore overlap capacitance, and we will discuss it and see what it is. The diffusion capacitance, on the other hand, can be at the source side or at the drain side, and we will discuss it later on. So, two main types of capacitance, the gate capacitance and diffusion capacitance. The gate can be classified into channel, or it comes from channel and overlap capacitances. Okay, now, so the gate capacitance, basically this is our poly gate here. This is the gate, okay? And the gate capacitances, in particular the channel, all right, it is the capacitance which is because we have here a channel of electrons, and the gate is charged positive, okay, and then we have here an insulating material, which is the SiO2. And as we say that anytime we have an insulating material between two conductors, we created a capacitance. This gate capacitance can be estimated, as we have seen earlier, as epsilon OX times the area, which is the width of the transistor times the length of the transistor, divided by the separation between the two conducting material, which is the poly and the channel, which is TOX. We said that we can lump these two terms in a new defined term, which is the COX here, times W over L, where COX equal epsilon OX over the thickness of the oxide. Okay. Now, it is important to notice that this capacitance varies by its value as the device operates, and we will see later on. Now, this is the channel capacitance. All right. Let's take a look at the overlap capacitance. The overlap refers to the fact that because the source and drain extend underneath the gate for a small distance, okay, there is a capacitance here between the gate, right, and the N plus, the gate and the N plus, right, and the N plus can be the source or the drain, and this is what we refer to as the overlap capacitance at the drain side or at the source side. As we said, typically this is a small, and typically it is ignored for practical reasons, but if you want to be accurate in your results, you have to include it in your gate capacitance. So the overlap as part of the gate capacitance typically is ignored. Now, the gate capacitance in general varies per operation, when the device is on and when the device is off. Okay, and let's use this table here, and let's use these two diagrams. This diagram on top here, notice that we are having on the y-axis the value of the gate capacitance, And notice that C naught is the maximum value. C naught is the maximum value, which is, we defined it earlier and an earlier slide. It is the E epsilon W L over TOX. That's the maximum value. Okay, as we vary VGS, of course, when we vary VGS, we are between the off and on for the device. If we are less than VT, if VGS less than VT, then the device is in the off state. And if we are above VT, then the device is in the on state. Okay. Now, notice that here the gate capacitance, has three components. So this is the gate capacitance: gate to bulk, gate to source, and gate to drain. Now, when the device is off, now notice that the gate to source and drain, they come in picture when the device is on. And the gate to bulk, it comes into picture when the device is off. Okay? Now, so when the device is at the cut-off region, which is this one here, notice that the value of the gate to bulk is about C naught, while there is no gate to source and gate to drain. You add these three together and you get the total of C naught. So the gate capacitance when the device is at cutoff equal to C naught, and this is what we see right here. Now in the linear region, when the device comes from the off state to the on state, notice that half of the capacitances is towards the source, okay, and half of the capacitance towards the drain. There is no bulk because this is when the device is off. So the gate to bulk is eliminated, replaced by gate to source and gate to drain. The total is C naught. Now, so if we look at this drawing here, what it tells us is that the gate to the gate capacitance, right? The gate capacitance is always equal C naught, right? And this is when it is off and when it is on. There's an interesting region here when around the VT. The gate capacitance dips here a little bit because of the depletion region and the changing from the on and off state, but it recovers and goes back to full C naught, because if we add CG to CD, we will get C naught as the total capacitance for the gate. Now the question is, as we are in this on, when the device is on, do we stay at C naught, which is the maximum value? And the answer is clear if we plot the capacitance versus VDS, because changing VDS, remember, changes me from linear all the way to saturation. It turned out when we start at the linear region, right, at the linear region, we have two components, the gate to source and gate to drain. Both of them equal C naught over half, as we have seen here, and their total is C naught. But as we go to saturation and we get the pinch effect toward the drain component goes to 0, and the source component enlarges to 2/3 of C naught. So you can see here the gate to drain is 0. The gate to source becomes 2/3 C naught. Of course, bulkhead doesn't exist because we are in the on state. And the total of the gate capacitance becomes 2/3 C naught. This means that as we go from linear to saturation, the total gate capacitance drops from C naught all the way to 2/3 of C naught. Okay, so that's an important conclusion here. Okay, now after that we will go to the definition of diffusion capacitance. Okay, so that's So the diffusion capacitance means what? What's the diffusion capacitance? It is actually it happens both at the source and at drain, and we will focus at the source here. It happens when the N plus material of the source touches the P material of the substrate. And there are two regions where this happens. It happens here at the bottom of the N plus and at the side walls. Okay. All right. So how do we compute this? So this is, I have some terms here clarified. So this diffusion capacitance between the source and the body. Okay, so this is diffusion capacitance between the source and the body, and you can compute it between the source and between the drain and the body as well. It is equal to the area of the source times this factor, and this factor is called the junction capacitance area. This is the junction capacitance area. So this is to get the bottom here, the bottom diffusion capacitance, and it is equal W times L. The area is equal W, the width times, I'm sorry, the D. So W times D, that's the area of the diffusion. So the D is the length of the drain or the source. Now, so W times D gives me the area, and then I multiply it with the CJBS, which is the junction capacitance per unit area, okay? And this CJBS is equal to CJ, okay, which is the junction capacitance at zero bias, multiplied by open bracket 1 plus the voltage between the source and the body. Why the source? Because we are computing the source to the body capacitance here, divided by the built-in potential, raised to this exponent, which is called the junction grading coefficient, typically MJ between 0.33 all the way to 0.5. Okay, so now, so this takes care of the bottom. Okay, how about we have this side wall here? So the side wall, we compute the perimeter times this factor here, and this factor here is called the side wall junction capacitance. The side wall junction capacitance, and it is computed by CJSW, which is the side wall junction capacitance at zero bias, multiplied by, okay, 1 plus the voltage between the source and the body, multiplied by the built-in potential for the sidewall, raised to minus MJSW, which is the sidewall junction grading coefficient. Okay, all right. Now it turned out that this sidewall, which is facing the channel, has a special coefficient. All right, so what we do, we compute the coefficient with the same way, right? But with the separate parameters where the j is added at the end. You see, this j is added at the end. This is just for this side of the perimeter. So the perimeter then will be modified to 2d plus w. And the W that faces the channel, we will multiply it with this special coefficient, which is this one here. But this coefficient for this perimeter, we will use this coefficient here, and the perimeter here will be W plus 2D. Okay. Now, so now here you notice that these two are the sidewall capacitance, and this is here the bottom capacitance of the junction. Okay, you add the two, the total gives you the junction capacitance for the source diffusion. Okay, let's take an example here. An example. The example here, it says calculate the diffusion capacitance between the drain and the bulk of a unit size contacted MOS transistor, and with that, what that means is that lambda equals 25, W equals 0.1 micro, D equals 0.125 micrometer. Okay, assume the substrate is grounded. Okay, and the diffusion region conform to the rules. Okay, and the transistor characteristic Cj equal this, Mj equal this, Cjsw equals 0.1, Cjswg 0.36, Mjsw equals Mjswg equals 0.1, and the surface potential, the built-in potential, and all the potentials are 0.7. Okay, so to calculate the drain, all right, we first calculate the bottom capacitance, and the bottom capacitance is the area, which is D times W, right? And here are the values for the D time and the D and the W. This is the D and the W. So we multiply them, and then we multiply it by the coefficient. Recall here in the example here, he's telling me that this is 0. So this cancels out, and the CJBS equals the CJ. So I plug in the number right here. And then I have the sidewall. So the sidewall, first of all, with 2D times, plus W, multiplied with the special parameter which is not facing the sidewall. And this one here, the W, multiplied by the parameter of the channel which is facing the channel. Okay, recall the parameter which is not facing the channel, it is right here, 0.1. The parameter which is facing the channel, it is right here, which is 0.36. It is important to notice that the parameter which is facing the channel is much higher than the parameter which is not facing there. So now we got this side and the other three sides. So this side is right here, okay, and the other three sides are right here. Okay, so you add the bottom capacitance, now you add the sidewall, and you get finally to this number. So he wants us to do this computation for two cases. The first case where VDD equals 0 at the drain, and the second case when VDD equals 1. And so this is the computation for VDD equals 1 volt, and I'll leave it to you to follow on with the computation, which is similar to what I have explained. Okay, with that we conclude the discussion of capacitances for the CMOS device, and thank you very much.